What is electricity? We're going to start out with a picture here of Benjamin Franklin, courtesy of Library of Congress. And electricity, in short, is the presence of charge, and it's typically the flow of electrons. All right, what does that mean? We're going to start first with the atom. Electrons are attracted to protons that you see there in the nucleus of the atom. And when there is a force, or sufficient force, the electron can leave the atom. Now, when this occurs across many atoms, electrons are going to flow and create what's called a current. Now, they might bump into other atoms, and that is known as resistance. This is a macro view, so let's shrink that down a little bit smaller because there are lots and lots of electrons that are flowing through the wires, electricity, that power the energy needs for our devices and appliances, such as turning on the lights. Now, the force that causes electron motion is referred to as voltage. Now, George Ohm discovered the important electrical relationships between voltage, current, and resistance, and you can see the letters given to each there, V, I, and R, and then also the effect on power, P. And it's called Ohm's law, and there's a wheel here, Ohm's law wheel, that's often used in electronics, and a bunch of different equations, but really comes from two simple equations, and the rest can all be derived from there. And one is the relationship of voltage and current and resistance, V equals IR, and the other is the relationship between power, voltage, and current, P equals VI. So remember those. But I'm going to make the argument here that we still don't understand electricity, and here's why. We know that electrical power can be converted to other types of power, such as mechanical power. And the question is, how does it do that? So let's take a stab at a new definition of electricity. Because everything is made of atoms, right? And atoms are made of particles, such as electrons. Electricity is the motion of a particle. Now, since all objects are made from these particles, all laws of motion can be traced back to the energy and the motion of a single particle. And let's explain each of these for electricity. Voltage. So voltage is a force. Right? When a force is applied on a mass, it causes motion. The larger the force, the larger the acceleration of that mass, such as this. All right, let's assume that to be voltage. Current, or amperage, is a velocity. Now, that's different than modern electronics because electron flow is measured as amperes, which is an electron charge called a coulomb passing through a specific point in 1 second. But let's flip that around a little bit. Instead, let's think of it as an electron with mass traveling at a certain speed and direction, which is velocity, like this. There, it's just moving. And it can be measured in velocity, such as meters per second, which is SI units. The problem is we can't see a single electron, so current is actually measuring many different electrons. They're traveling at different speeds and directions, so really what we're looking for in current is the average velocity of all those electrons put together. Now, resistance. Resistance is a measurement of current opposition, right? It occurs when electrons collide with other atoms, such as this, and that causes a vibration of the atom, which is measured as temperature. That's what temperature is. It's basically the measurement of a vibration of an atom. And that's why heat is caused in resistors. In any case, in modern electronics, resistance is measured in ohms. But here, let's change this around a little bit and refer to it as a measure of mass flowing in a given time frame. I'll explain that more in a little bit. But first, again, because there's many different electrons, we have to think about electrons as some are going to be blocked, such as the one on the bottom, and others being able to get through. Now, power. Power is energy over time. It can also be expressed as force times velocity. When the classical laws are applied to the motion particles, it becomes much easier to understand how power is transferred like this, because the power is the sum of all particles under a force moving at velocity. So we're going to prove this. Right? It's pretty cool, right? Electric electricity in the quantum world can be described with the classical laws of physics. That's a bold statement. So where's the proof? Right? In the following, we're going to present these three things that you see there as the proof. So let's get started first with units. Because in math, nothing works unless the units align properly in an equation. Now in EWT, which is energy wave theory, electron charge, or coulombs, is replaced with meters. And here's why. In EWT, the electric force is traveling longitudinal waves, and these waves can be constructive or destructive based on other particles in vicinity, and that's what causes a larger charge, for example, if they're constructive. And how is wave amplitude measured? Right, it's a distance. Think about a traditional wave. How do you measure its height? Well, it's a distance. So in this case, the SI unit is meters, and so coulombs has been replaced with meters. And if you need further proof, there's 22 fundamental constants in physics that were all simplified using the same approach. You can see the URL. And here we have it. Here's how the units work out when you compare electrical and mechanical, right? So it's going to start first with current, because current, which is A for amperes, is really a coulomb per second. So C is coulomb, and now if you replace that with M for meters, it becomes the same thing as velocity, meters per second in SI units. Full derivations on the right-hand side. And the other three, once you have that, become much easier. Everywhere you see an A for amperes, you replace it with meters per second. And lo and behold, voltage is a Newton, which is expressed as kilogram meters per second squared. Newton's just an easier way to say it. And power is watts. Again, same SI units there. And resistance is the same strange thing called kilograms per second, which again I'll explain in further detail on an upcoming slide. But there you have it. This is how the units would align. Let's get into the relationship now. Physics is really simplified if you think about the motion of a particle. And so Newton's law can be related to Ohm's law. And very specifically here, we're talking about Newton's second law of motion. And in this law, F equals ma, a force of a ball, let's imagine a 1 kilogram ball being dropped on Earth, and I've simplified it here to 10 meters per second squared, rounding up. It's the force of that 1 kilogram ball is 10 newtons, or full SI units that you see there. And after 2 seconds, the velocity can be calculated. And in this particular case, it's 20 meters per second. All of this is known and done on a regular basis using Newton's equations today. But now we're going to make it a little bit trickier. Let's imagine 2 balls being dropped, and one ball hits before the other ball reaches its final destination. So one hits at 1 second, and the other hits at 2 seconds. And so the velocities are going to be different. And we're going to average out the number of balls, given a variable n. In this case, it's only 2 since there's 2 balls. And the velocity of one is calculated to be 10 meters per second. The other is 20 meters per second. And simple math, the average is 15 meters per second. All right, that's an example of Newton's law. So how does this relate to electricity? Let's come back to Ohm's law. Now let's imagine the same thing. Let's imagine an electron traveling in a wire. I'm making this really simple, so let's assume that electron mass is 1 kilogram. It's not, but I could have made the ball you saw in the previous one 9.1 times 10 to the minus 31 kilograms, but the math is much simpler this way, so let's just make it easy. And that electron traveling now in a wire has resistance, and resistance again is a measure of how much mass can travel in a time frame. So for the mass of the electron, which was simplified to 1 kilogram, it traveled 2 seconds. Therefore, the resistance is 1/2. And current can be calculated now from Ohm's law, V equals IR. In this case, we have to flip it around and say I equals VR because we're V over R because we're calculating current. And when you do, what do you know? It's the same thing as that first example we showed earlier. It's 20 meters per second. It's the exact same thing as Newton's law. It's pretty cool. But that was a simple one, so let's expand on this now. Ohm's law is really a calculation of many electrons because you can't just take a look at one electron and calculate it. It's impossible. So imagine two electrons, one collides with an atom after 1 second. Now, does that look familiar? That's the same thing that we just did with Newton's law with two balls that are being dropped. The total resistance in this case now is the sum of all masses divided by the sum of all time, and you get 2/3 kilograms per second. You can see the equation there. Now, current, first step, of course, is to calculate the current for each of those electrons. First one was 20 meters per second. And if you do the same math on the second one, it's 10 meters per second. And when you average those two, what do you know? You get 15 meters per second. Again, it's the same thing as Newton's law, the example we just showed. It's pretty cool. Now, if you think this was too simple, because I just used only two and very simple numbers, you can try this for any combination of electrons at different distances. It's always going to be the same, no matter what, even though I've done a very simple example here for the presentation. Now, because we can't measure and calculate every atom, we measure a collection of electron properties, and we gave them names like ohms and amperes. So in this case, the current is 15 amperes, and the resistance is 2/3 ohms. But again, it's really simple when you think about it in terms of standard SI units. It's a velocity, and it's kilograms over seconds. And we measure voltage according to Ohm's law, right? The voltage is really the average current and the total resistance there. And what do you know? You get back to that same voltage, that force, 10 volts. Now let's finish this up with mechanical power, right? Mechanical power is described as any energy over time, which can be thought of as a mass, accelerated over a distance in a given time. That's the way that I like to think of power. It's much easier to think of mass accelerated over distance at a given time. But what is that? That's really just a force times velocity. It's all one and the same. But I'll give you an example. Right, lifting a mass of 15 kilograms, that boy there on the escalator, if you want to lift him up against Earth's gravity for a distance of 1 meter in 1 second, that's 150 watts. That's how to do the calculation for mechanical power. Now, electrical power is calculated as voltage times current, P equals VI. Now, imagine a collection of electrons equals 1 kilogram of mass. That's much better than my example where I assumed a electron was 1 kilogram. Let's just assume the collection of these, all 1 kilogram, all moving across 15 amperes. And this is what the equation looks like. And again, we get to 150 watts for that power. It's 10 volts times 15 amps. Now let's put all this together. And because now we can understand how power is transferred. Electrical and mechanical power is really just the energy calculated as the sum of all particles, and energy is always conserved. I'm assuming the same time frame here because I've set the mechanical power equal to the electrical power, but these are all the numbers from the previous slides, and I put the units in here because the value and the units now all align for mechanical power and for electrical power. And why? Because we thought of it as the motion of a single particle and expanded it out, in the case of electrical power, for the motion of a number of different electrons running through a wire, and then acting on more particles, which are essentially building atoms, forcing a body such as that boy who's 15 kilograms up. And that's how it works. Everything comes down to one set of laws. Electricity is the motion of charged particles, like the atom, like the electron. Newton's laws of motion apply to objects, which are made of particles. So when the classical laws of physics are applied to particles, and the summation is taken for the total particles in an object, we find that everything can be expressed from the motion of a single particle. One set of laws. That's cool.